So we resume with the talk by Aleksy Tralle on non-virtually abelian discontinuous group actions versus proper SL2R actions on homogeneous spaces.
Thank you very much. Do you hear me? Okay. So first of all, I would like to, as one of the organizers, I would like to thank all the participants for coming here. The next thing is that because in fact this it's a program, it's not a standard conference, it's a program of ECTS. So we decided, as organizers, we decided not to have empty slots. So because of that, I am giving this talk. So I apologize for ad hoc talk, which was somehow not very much prepared. So I hope you'll forgive me for that. So and then let me start. Here is the title. That again, let me stress that it's a joint work with Maciej, who is here, with Willem de Graaf and Piotr Jastrzębski. So sorry. So well, I will. My talk will be will consist of 3 parts. First, I just formulate the problem, which is somehow interesting but rather particular. It is somehow it's experimental work, and you will see why I'm saying that it's experimental work. So, well, I will recall, of course, but only formally, because we had a very wide presentation of Clifford-Klein forms by our colleagues, by Toshi, by Maciej, and by Joske. So I think it makes no sense to repeat all this again, but nevertheless, this is a definition of a proper action. So an action on topological space, or topological group G on a locally compact Hausdorff space is called proper if this condition holds. So this set is compact, very compact S. Or equivalently, an action is proper if the map of this type is a proper map. So the preimage of any compact set is compact. All this was presented, and the examples were also shown. So I will skip it and just say that in the due course of this talk, we will get examples as well. So so again, we fix semi-simple Lie group, closed reductive connected subgroup, and a discrete subgroup. Then this space is called a Clifford-Klein form if gamma acts properly and freely on G over H. If this is compact, then we get a compact Clifford-Klein. Or we also say that gamma is a Clifford-Klein form for G over H, and that G over H admits a compact Clifford-Klein form. Notice the assumption that gamma acts freely is not very significant. It was explained by Kobayashi. But nevertheless, there are questions. When does a large discrete group, subgroup of G, act on a homogeneous space properly? And the second question, when does the homogeneous space G over H admit a compact Clifford-Klein form? So, well, then again, question 2 was widely discussed in talks of Kobayashi, Morita, and Bohensky from different perspectives. So we can single out general criterion of Kobayashi, which is expressed via the action of the little while group in the cohomological dimensions. We were somehow now aware of topological abstractions obtained by Morita and Tolozan. Also, we analyzed standard Clifford-Klein forms described in terms of the algebra decompositions. This is Maciej and myself. And non-standard Clifford-Klein forms, we also were, non-standard Clifford-Klein forms were shown by Kassel, Morita, and Tolozan. So question 2 was discussed on this conference quite widely. But question 1, more specifically, we want to examine the connection between the following 3 conditions. C1, the space. Okay. So more specifically, we want to examine the connection between the following 3 conditions. C1, the space G over H admits a proper action of an infinite discrete subgroup of G. C2, the space G over H admits a proper action of a non-virtual abelian discrete subgroup. And C3, the space G over H admits a proper action of a subgroup locally isomorphic to SL2R. So obviously C3 implies C2 and implies C1. And because, say, working on these questions, I always forgot which is which. So I've written here for you. So you can always check that C2 is non-virtual abelian and C3 means that there is a proper SL2R action. Okay, why these relations between such actions C2 and C3 in particular are interesting? Well, I will give several reasons. Well, I will begin by citing some results which are known. So for many important classes of homogeneous spaces, C2 and C3 are equivalent. For example, we have a theorem of Okuda from 2013 that for the semi-simple irreducible symmetric spaces G over H, conditions C2 and C3 are equivalent. We call G over H strongly regular if this A it's a Cartan subspace. I will notation will be fixed later, so it's just an introduction. So we already seen all this. So then there is a notion of strong regularity of the embedding of H into G, and then the theorem of Bocheński is that for a strongly regular homogeneous space G over H, such that the real rank of H equals the A hyperbolic rank of H, then again we have the condition of equivalence C2 and C3, if and only if the A hyperbolic rank is of G is larger than the real rank of H. I will explain all this later, but just that, well, there are to sum up, there are some conditions on homogeneous space which tell us that C2 and C3 are equivalent. On the other hand, there were known exactly two examples of spaces which fulfill the condition C2, but not C3. So one example was given by Okuda. There exists a three-dimensional split abelian subgroup H of SL5R, such that G over H is C2 space, but not a C3 space. And again, the theorem of Bocheński that there exists a three-dimensional split abelian subgroup H of G, which is equal SO44, such that G over H is C2 space, but not a C3 space. Okay, these are some small motivations, and how this one more motivation is how these examples were found. Well, in fact, there is a criterion of proper actions for proper actions, this say Kobayashi criterion, which expresses the condition of properness in terms of the little while group. And because of that, if you have something very simple, then you can just apply this criterion. And so these are examples which were found. So it's just finding an appropriate subspace in a Cartan space such that the action of W on this subspace, the image does not contain B. B will appear somehow. So everything will appear. But anyway, the point is that it is somehow, it can be checked because M is abelian subgroup of, say, so on one hand, we see that for spaces G over H of reductive type, we have the following. There are no implications. C1 doesn't imply C2 and doesn't imply C3. But the subgroup, which is very specific, yes, it's an abelian subgroup. We would like to understand somehow what is going on with these two conditions. And well, okay, there are some related facts and questions. A semi-simple symmetric space admits a non-virtually abelian properly discontinuous action of a subgroup gamma, if and only if it admits a proper action of a three-dimensional simple Lie subgroup of G. So for the class of symmetric spaces, C2 and C3 are equivalent. This is Okuda's theorem. And for necessary and sufficient, people would like to find, it's an open problem, find the necessary and sufficient conditions for G over H to admit a proper discontinuous action of a surface group for the genus greater or equal to 2. So there are some related facts and questions. So we somehow, this partial explanation why we want to understand this relation between C2 and C3. But I will now come to my main motivation why I became interested in this question. So these are the data which now I would like to fix. So from now on I fix my data and we will use it all the time. So the data are, if you have our semi-simple G, K, sorry. K plus, excuse me, please. Yes, K plus. So of course, instead of H, you should write K, and it means the maximal compact subalgebra in G. So Cartan decomposition, and we have a compatible decomposition of Cartan decompositions for H. So this KH is in K, and the subspace PH is in P, and then the Cartan subalgebras also are included in that way. So we fix these Cartan decompositions for G and for H, and they are compatible. The next, we have a restricted root system. Restricted root system means that you take the complexification GC and then the split Cartan subalgebra and restrict complex roots to A, and then you get a restricted root system, which is also a root system in the usual way. And then we fix the little Weil group. So it's a normalizer of A divided by centralizer of A. And then we know that W acts on A by orthogonal transformation as a finite group generated by reflections in the hyperplanes determined by simple roots. Take the longest element and then define this set. It's a cone, it's a B plus, which consists of such X which satisfy this condition, and then take just the linear span of it. This is our B. This is our subspace B. Yes. A plus, I didn't say this, yes. A plus is a Weil chamber. A plus is a Weil chamber. So this I fixed my data. And then what is, I would say, my main motivation, so for me, maybe not for Maciej. This is a theorem of Benoit. So Benoit theorem is that GH is C2 if and only if for every element in the little Weil group, V times AH does not contain B. This is, you see, this is a formulation of C2, which is completely expressed in terms of root systems. Yeah, moreover, one can choose a discrete non-virtual abelian subgroup of G acting properly on G over H to be free and Zariski-dense in G. So this is the I will explain you now why I'm so interested in this theorem. So let's look at this. So this is a criterion for C2. This is a criterion for C2. Then main question, which is experimental. Create computer algorithms and programs which verify C2 and C3 for general semi-simple homogeneous spaces and use this to understand property C2 versus C3. And well, the sum up of what we have done is that algorithms and computer programs are created using computer algebra package GAP4 and tested on the database of the graph and Marani. There is some database of subalgebras in simple Lie algebras, which created by the graph and Marani, and new homogeneous spaces which are C2 but not C3 found in this database. But from this experimental work, you will see that it's quite difficult to find. And still there are two more examples, which you cannot do by hand, but nevertheless, somehow they show that something interesting happens. Yeah, we don't know what exactly, but something interesting happens because you will see. So here is our theorem. Also a joint work, as I told you, this is a joint work with Willem de Graaf. Assume that G over H is a homogeneous space given by the following real embeddings. These are split exceptional Lie algebras, E77, E88, and the subalgebras are written, so SL2R plus F44. So all are split. Everything is split. Or F44 and G22. In both cases, HC, let us also just note that in both cases, HC is maximal in GC, where HC and GC denote the complexifications of HG respectively. So if these are two, then GH is C2, but not C3. So this is what happens. Not this is test result, because as I told you, in fact, what we did, we created algorithms and computer program to verify Benoit condition, which might be of general interest. This computer algorithm, our algorithm, which I will explain. But then this is a theorem, but it is a theorem. Although it was done by computer, it's a theorem. The appropriate verification was done. And so it's the first test result and the second test result. Let GM be the graph Marani database. I will explain it. So this Marani database consists of real forms of complex embeddings with maximal subalgebras. So the subalgebras are maximal, of complex simple Lie algebras of rank less or equal to 8. So this is a huge database, already huge database. And then for the theorem is that for any G, the pair GH from the Marani de Graaf database, such that the rank is less than 6, conditions C2 and C3 are equivalent. Yeah. Yeah. Well, if you want something better than Abelian subalgebras, I think it's no chance to do it by hand. Some idea, maybe some idea, but it's experimental work. And so, and here is the observation. The assumptions of H being maximal in G is very interesting in the context of searching for homogeneous spaces, which are C2, but not C3. On one hand, one should expect that homogeneous spaces which are not C3 are given by large semi-simple subgroups. So they must have as large real rank as possible. But on the other hand, we are restricted by condition C2. So we cannot take the subalgebras of equal rank. So it's a subtle thing that you cannot take of the same rank, but we can have such. So this is a subtle interplay between C2 and C3. It cannot be too large, it can be too small. Okay. So part 2, these are tools to prove this theorem. So properness criteria and numerical characteristics. As I said, that basically our algorithms verify Benoit criterion, but we also need some other tools which were explained by Kobayashi. So I just mentioned them: properness criteria and numerical characteristics. So criterion of properness. So now let's fix the same as before, but now take two subgroups HL, which are connected reductive subgroups of G. And then you see that all the assumptions are the same, but now we take a pair H and L. And then we also take the compatible Cartan decompositions. And then the theorem Kobayashi, which was also explained by Kobayashi in his talks, that the following conditions are equivalent. H acts on G over L properly, L acts on G, H properly, and then the condition on Cartan subspaces AH and AL is that they intersect at 0. Moreover, the subgroup L acts properly on G over H only if the conditions on ranks is satisfied. So this inequality of ranks. This criterion of properness. Cartan map, which also appeared. Here is you take the system of restricted roots, Cartan decomposition of G, and define the map. Well, as you can see on the slide. So Cartan map should be used. Then criterion also known already for us, yes, criterion of properness. And so, of course, we again mention, as usual, the Calabi-Marcus phenomenon. So, and now one more invariant, numerical invariant, which I will use, is a hyperbolic rank. So it's just dimension of the subspace B, which was introduced. However, well, it's very often it coincides with the real rank, but not always. And then I wouldn't like to explain much about how to calculate it. Let me just show you the table. That if these Lie algebras are simple, then here is the table of Lie algebras which have different real rank and a hyperbolic rank. So this is, for example, so you can think about this just that way. Then no, it's the rank of this subspace B. Okay, maybe. No, it's here. Yeah. So, sorry. Here it is. Oh, here. So it's in Cartan subspace. It's in Cartan subspace. So and then what is needed? Yes. Now I'm going there because so this is the definition, and this is the list. See, for example, E6, the real rank is 6, and the a hyperbolic rank is 4. Okay, but anyway. Yeah, in most cases, this is exactly the table where it is different. Otherwise, it is the same. Otherwise, they coincide. So what was the question? Sorry. Yes. Sorry, I didn't understand the question. Okay. Yes. Yeah. Most cases, yeah. So, and then, yes, and then the theorem which we use, which proved earlier. So if the a hyperbolic rank of H is equal to rank a hyperbolic rank of G, then G over H is not C2. And if rank is if a hyperbolic rank is greater than the real rank of H, then GH is C2. So we can use it. Okay. And the part 3, algorithm programs and proofs. So, okay, approach. So what we do? We have used the database of Marani and the graph, containing all real forms of maximal semi-simple subalgebras, of complex simply algebras of rank up to 8. Maybe I should say more precisely that this database consists of embeddings of H into HC to complex embeddings of maximal subalgebras in GC in the complex case, but then Marani database is about all possible real forms of these embeddings. So we have filtered the database using some additional results according to the previous slide. So checking the hyperbolic rank or making a detailed description in the case when real rank is 1. And we have used an algorithm. I will explain why we need it. Use an algorithm which gives an embedding of H into G such that AH is in A. The problem is that the classification or database consists of these pairs H and G, where H are classified up to abstract isomorphism. So there may be different embeddings. And so we are not saying that we use that we can prove for any embeddings, but only for embeddings which are in the table, in the database. But then, if you take the standard representation of this database, then AH may be not embedded into A, and then you need a special algorithm to find AH which is in A. We have used the classification of nilpotent orbit and criteria for proper actions. And then we somehow filter everything and get the result. And then difficulties. What are the difficulties? We need to compute the root system of G with respect to the space A. However, in some but not many cases, this required eigenvalues that did not lie in the ground field that this is a package which we use. And then if it's not our ground field, then we cannot use the package. So for a few cases, our procedures could not be used. And when G is a split form of type E7 or E8, the orbits of the little while group of elements of A corresponding to nilpotent orbits can be very large. In this case, we can handle large orbits by using an algorithm due to Snow for running over an orbit of the Weyl group without computing all of its elements. This algorithm has been implemented in the core system of GAP4. So then to tell the truth, it's like you run down your program and somehow hope that at some point it will stop, and it did. In 2 cases, in this case, computer did this. So now maybe some details. I still have time, so some details. Verifying C3. We need some reformulation of Kobayashi's criterion just to adapt it, just express it in a way which is easy to somehow to write down after as an algorithm. So a triple HEF of vectors in G is called an SL2R triple. If you see it's just SL2R embedded into G. And then the theorem is that let G and H be semi-simple groups with the algebras G and H. Let G equals K plus P be a Cartan decomposition of G, and assume, as we may, that H is compatible, has compatible Cartan decomposition of H. Let A be a maximal abelian subspace. Let HA in this be a maximal abelian subspace with AH is in A. Let L be a subgroup isomorphic to SL2R with the algebras L spanned by H, E, F, and H is in our Cartan subspace with the usual commutational relations. Commutational relations are above. let W be the little while group of G with respect to A. Then G over H admits a proper action of L if and only if the orbit WH has no point in AH. So yeah, algorithm for C3 finding AH in A. So the first difficulty, which is somehow we managed to do. Let AH be a maximal abelian subspace. Set A hat A equals AH, and while the dimension of hat A is less than dimension of A, do the following. Compute the centralizer, fix X in this intersection of the centralizer and P with X does not belong, with X not belonging to A hat, and replace A hat by the subalgebra spanned by A and hat and X. And then set, when we apply this procedure until the dimension will agree, then set A prime equals A hat. This works because any abelian subspace of P lies in a maximally normal, maximally abelian subspace of P. So the spaces Z always contain a maximally abelian subspace. Now we write A instead of A prime and assume that AH equals this, and it is a maximal abelian subspace of AH. And then algorithm for C3, weighted Dynkin diagrams. So we need the relations between subalgebras isomorphic to SL2R and nilpotent orbits of G. This is a well-known Jacobson-Morozov theorem. So the nilpotent orbits in GC are parameterized by weighted Dynkin diagrams. So I wouldn't like to explain much about weighted Dynkin diagram, but of course it's just, there are labels on the usual Dynkin diagram. And each weighted Dynkin diagram uniquely determines an element H in a given Cartan subalgebra of GC. This H lies in a non-uniquely determined SL2 triple HEF. So take the adjoint group of GC, and then the above construction gives a bijective correspondence between the list of weighted Dynkin diagrams and the conjugacy classes under this joint representation of subalgebras of GC that are isomorphic to SL2. And finally, a nilpotent orbit in GC has points in G if and only if its weighted Dynkin diagram matches the Satake diagram of G. Moreover, these are precisely the nilpotent orbits having SL2 triples lying in G. So here I also do not want much to tell much about this how to say matching. But here is, for example, of weighted Dynkin diagram. This is say an example of Satake diagram. Black roots are those which project onto zero on the Cartan subspace. And then matching means that here should be zeros which correspond to black nodes. So it means that the compatibility then means that this must be zero and this. And of course, in general, you need also, if there are arrows in the Satake diagrams, then this must be symmetric, but here we have no black nodes. So anyway, these are data to check, in fact, to check Benoit condition. So algorithm for C3, also procedure. So the procedure is obtain the list of weighted Dynkin diagrams of GC. For the weighted Dynkin diagram that match the Satake diagram of G, compute an SL2 triple HEF with H in A. Let H denote the set of all elements H that are obtained in this way. For each H, check whether WH intersected with AH is empty. If this holds, then the subgroup of G corresponding to the subalgebra spanned by an SL2 triple acts properly. If the intersection is not empty for all H, then G over H does not admit a proper action of a subgroups locally isomorphic to SL2R. Verifying C2. compute the little while group and hence its longest element. Compute a basis of the space B. By running over W, we can check whether there is a W such that WH contains B. The space G over H is C2 if and only if there is no such W. Implementation. We have implemented the two procedures for C3 and C2 in the computational algebra system GAP4 using the package, so the special package CoRelG. This package has a database GM, which, so the deGraff Marani database, which was computed by deGraff and Marani. Also, we use the SLA package, which has lists of weighted Dynkin diagrams for the nilpotent orbits of the semi-simple complex Lie algebras. Note two things. If you find H such that this intersection is empty, then we can stop. If it is not true, then when enumerating the orbit, we can reasonably hope to find an element in the intersection rather quickly due to Snow's algorithm. So in practice, it usually suffices to enumerate only part of the orbits. And it yielded new examples for E7 and E8. Exactly this happened. We ran down. Oh, huge. For E7, I don't remember, but it's really huge. Means in computer sense, not in... or something like that, I guess. Yeah. Well, finally, the computation was not so long. Yes, I don't remember, but and Mati is checking. But anyway, it took something like 1 hour or something like that. So yeah, yes, exactly this, exactly without story. Okay, so in practice, it usually suffices to enumerate only part of the orbits. And then we get this implementation and computational results. The package CoRelG contains a database of maximal reductive subalgebras, maximal. This is, again, I would say that it was a kind of my motivation because to do this experimental work, because it's a lot of activity in classifying maximal semi-simple subalgebras in simple Lie algebras in a complex sense and in a real sense. And there are huge databases. And this is say physicists like this very much, and so there's a lot of activity of doing this by computers. So you can take a lot. This database is in this package, and then it gives maximal reductive subalgebras of the simple real Lie algebras up to rank 8. We have used our implementation to check whether G over H is C2 and C3. We have checked C2 and C3 for non-compact G of rank up to 6, and for G equal to the split forms of type E7 and E8. For the simple G up to rank 6, there are 42 maximal semi-simple subalgebras in total. We found no examples of G over H that were C2 but not C3. Of this, subalgebra 13 could not be dealt with by our programs, or for the reasons which we have described. Yes, the field is not in the CoRel G. So because of that, we list them in the tables. These are exceptions which are not dealt with our programs. So this is the table, but then this is the table, but then we can analyze this table, and 9 of the spaces from this list do not yield G over H, which is C2 but not C3, by theoretical considerations. First, either they have equal real ranks, or rank is 1, which is less than a hyperbolic rank, and the result follows from the classification of nilpotent orbits. The following homogeneous spaces from the table are not covered by these arguments. So SP33, the pair SL2R, SU13, SO46, SO23, and this exceptional pairs. So these are not covered by 1. So we need to apply one more procedure to verify that these spaces are C3. And this is another another procedure. So we prove the following proposition, and the proof is by computer. Assume that G is CP33, G is SO46, or G E62, and let H be an arbitrary reductive subalgebra with rank 2. Then G, the pair GH corresponds to a homogeneous space G over H, which is C3. Then, surprisingly, but you need computer to do this. And then here is, say, stupid algorithm which needed to be corrected. But this algorithm, you can just look how it works. And then I won't show you the true algorithm. So proof, write down all weighted Dynkin diagrams for GC which match the Satake diagram for G. Write down vectors whose coordinates are read off the weights of the weighted Dynkin diagram. Here T is the number of the non-trivial weighted Dynkin diagrams of GC which match the Satake diagram. If some are on the same line, then choose only one. Check if there exists W1, WK in the little while group such that these vectors lie in a two-plane. If this W1, WK do not exist, then G over H cannot be not C3. This cannot be implemented directly because the number of operations would exceed 10 to the power 60. However, one can modify it. It would require some details which I would like to skip. However, one can modify it and write a program with a number of operations quite easy. And running it down, we get the result. So the idea is as on the slide, but it needs some modification and some proof that it works. And so I will just stop here, just addressing to some sources. So first, in our paper, which is on archive, there is an ancillary file with a program, so you can use it. And then just the source of our say computer algebra system. This is GEP group, so this you can also find this. Okay, so I somehow finished. Thank you very much, and I apologize for this experimental work, which is somehow a bit different in style. Thank you very much.
So, there are questions? Please.
So, can I ask one question? So, if you take a complexification of your example,
Yes.
Is it also the example or not?
I don't know.
Okay, I think so you are working on a split case so that the C2 condition is the same.
Yeah, So I wouldn't say, I would expect this, but I wouldn't like to say yes.
But
decisively. But anyway, yes,
I'm not sure about this C3.
because it's split. It's split.
Other question is, do you have any idea to obtain infinitely many example of C2 but not C3?
That's the point. It's really, you know, it's a bit mysterious. Yes?
Yeah.
So the only thing that I can say is that probably the while group should be complicated. So this exceptional case is better, I guess, than the classical case.
Yeah.
But that's the only my intuition about that. But because after
then,
all these efforts, we found 2 new examples, but you cannot certainly do it by hand. E7 and E8, you cannot do it in another way. So that's what I think.
But if you seek for the semi-simple example, then there are only finitely many examples in exceptional.
Yeah. It might be good idea is to think it that way, just to try to understand the while group. Yeah, that's it.
Thank you.
Thank you.
Yeah, so you say that here this becomes overly computationally intensive, and here again the problem is that in the point 4 we need to go over a product of the Weil group, right?
Yeah.
Mm-hmm. Thank you.
For semi-simple symmetric spaces, we know that C2 is equivalent to C3. I cannot catch. Oh, you mean? Similar. Oh, I understand. Okay, so it's just you have a semi-simple Lie algebra or semi-simple Lie group and involutive automorphism. So you don't. It is not Riemannian. It's pseudo-Riemannian. So yeah, this is semi-simple symmetric space in the sense that G is semi-simple, H is semi-simple, but you don't require H to be maximal compact, so it's not Riemannian. It's pseudo-Riemannian. Yes, these are fixed points of involution. Still, this is pseudo-Riemannian symmetric space.
Thank you. There are other questions? So if not, we thank all the speakers of this afternoon.